All right, so we have one more simple machine. All right, guys, listen. So a lever is the last one, and we're going to talk about levers today. We'll talk about the different types of levers and some examples of each type. So a lever is basically any sort of rigid object that pivots on a point which we call the fulcrum. So that's what a lever is. And you can set up levers in different ways, and we call those the different classes of lever. Often, but not always, a lever can multiply the force that you're applying, like many of the other simple machines. It can allow you to lift an object using less force. We call the levers by their class. There's three classes of levers: first, second, and third class lever. And they're all set up in different ways. When we are using a lever, we have a fulcrum. It's the point on which it pivots. Okay. We have a rigid bar. And we have, what would we call this thing we're going to lift? The resistance, or the load. Okay. And we have to apply what?
Force.
What kind of force? Effort force. All right, so to help you to remember the different classes of levers, if you remember the word free, you ignore the last E actually, it doesn't matter. But if you remember the word free, a first class lever has the fulcrum in the middle. So, for example, I have, what is this? Resistance. What's this? And this is going to be my effort. So here, what's in the middle of those three things? The fulcrum. This is a first class lever.
Wow. Snazzy.
A second class lever, so the word free, has what in the middle? Resistance in the middle. So we can have our resistance in the middle, our fulcrum here, okay, and I can have my effort here. That is a second class lever.
Wait, like, what would be the point of that? Because you still have to get it, like, on the thing, so you still have to use the same amount of force. And then, like...
So if I, we'll get to this, we're going to go through each lever one at a time, and I'll show you the point of it in a minute. But it's really the same point as the other, as a first class lever. And then finally, third class lever, what's in the middle?
Effort.
My effort.
That seems like it's going to be the hardest.
It is harder.
Good
Good question.
It's harder.
We have to think about our constant trade-off. Yes, I have to put in more force.
Do it for less distance.
Yes. So how much, so we were going to wait and talk about this. If I do this, how high do I actually lift my hand? Not a lot, but look at the resistance. Right? I only move my hand a little amount, but I lift the object very high. The difference is I have to use a lot more force to do this. So this type, the third class, is actually not multiplying your force, but it's multiplying the distance you're lifting the object. I could lift this object very high, even without lifting my hand very high.
Have you ever seen those videos on YouTube where it's like an adult and like a really small kid using like a first class lever, and like the adult like jumps on the other side and the kid goes flying?
No, that sounds a
That
little.
works like a water.
That sounds cruel.
Yeah, like a water You're small.
Yeah.
Like a match.
All right.
Or like
Like a water, but it wouldn't
Air mattress.
Yeah.
Yeah, air mattress.
All right. So here we have our levers: first, second, third class levers. So you got to remember the word free to remember which class lever is which. Okay. Here we have a first class lever. Again, first class lever has the fulcrum in the middle. And a first class lever allows us to multiply our force. Allow us to exert much less force, depending on how we set it up, to lift an object. So here I have, this would be an example of a first class lever. And so to lift this object using this first class lever, how much force am I going to have to apply here? Look at this example I have up here. How much force do I have to apply?
A lot.
Not
Not a little. Not a little.
20 newtons.
Very little.
But it's gonna take.
However,
But what's, again, my trade-off, how far am I going to have to move this?
A lot.
A lot. And how high up, how much am I lifting the resistance? Not very high. It's our constant trade-off. So the closer this fulcrum goes to the resistance, the more the mechanical advantage. Like if you could even set it up so that it balances out if you get this right in the center of gravity. Okay.
I'm really doing that with my pencil.
On your finger?
Yeah. I'm like on your.
All right, so yeah, it's sliding a little bit. So anyway, we calculate, when we're calculating the mechanical advantage of levers, the calculation, the formulas are obviously the same. Ideal mechanical advantage is effort distance over resistance distance. So where do we get those variables? The effort distance is the distance between the fulcrum and where you exert the effort. Kind of makes common sense. The resistance distance is the distance from the fulcrum to the resistance. All right. For actual mechanical advantage, we just use the forces. So the resistance force is the weight of the object. The effort force is the force we need to use the machine. All right, so ideal mechanical advantage, what's ED for this simple machine? This lever here? Effort distance is 150 centimeters. Resistance distance, 50 centimeters. Giving us an ideal mechanical advantage of 3. Actual mechanical advantage, what's our resistance force?
50 newtons.
50 newtons. What is the effort force? 20 newtons.
2.5.
Giving us, does that make sense? Yeah, this is an example that makes sense. Actual should be less than ideal. However, if you think about this, how close do you think they'll be?
Really close.
Pretty close, because how much friction is there really in this simple machine? There's just the friction between this small part of the ruler resting on the fulcrum, so it's actually not a huge amount of friction, and therefore our actual and ideal should be relatively close. Not like the other, like the inclined planes we used when it was significantly less, or even some of the pulleys, there was a significant amount of friction. So those are first class levers. Okay? Start carrying myself. The seesaw. A crowbar. So if you think about a crowbar, if I'm prying up a nail or the end of a hammer, the resistance is the nail. It pivots on like the curve of the crowbar, and you push here to pry up that nail. The way that works is because you're multiplying your force. You're exerting a force here, and it's being multiplied to pry that nail out of the wood. The longer the crowbar, the longer the handle, okay, the more mechanical advantage it's going to give you. Okay. A smaller, so like if you have the end of a hammer, which is like a crowbar, you have to exert a pretty hard force to remove the nail. Whereas if you have a very long crowbar, you exert much less force because of the length there, because of the resistance distance and the effort distance. Okay. A bottle opener. Okay. To open a bottle, the fulcrum is actually the little thing that goes on the lid, and then you're exerting your force, the hand, and the resistance is the top of the bottle. Okay, so you guys asked, did you ask about this earlier? Second class lever. So what's in the middle? The resistance is in the middle. So you guys said this, like, how does this help you? Well, it helps you in a similar way to the first class lever because I can lift this object using very little force. But again, I have to lift my hand a long way to just lift the object a short amount. And as the resistance gets closer to the fulcrum, our mechanical advantage increases. The variables remain the same. Effort distance is from the fulcrum to the effort. Resistance distance is from the fulcrum to the resistance. All right. So in this simple machine, Matt, what's the effort distance?
120.
120 centimeters. What's the resistance distance, Will?
40.
40 centimeters. Giving us a mechanical advantage of? 3. In this simple machine, Karina, what's the resistance force? 70 newtons. And Luke, what's the effort force? 30 newtons. Give me some mechanical advantage of 2.3. Examples? A wheelbarrow. So if you imagine a wheelbarrow, the fulcrum is actually the wheel. That's where it pivots from. You exert your force in the handles, and the load, the resistance, is in the middle. It's a second class lever. So when I was, between 16 and 22 years old, I used to work road construction with my grandfather and my uncle. We used to rebuild roads and stuff. One of the things I had to do was mix cement and then put it in a wheelbarrow and bring it to the manhole we were working on. And so if I had a full wheelbarrow full of cement, it was really heavy. So what I would try to do is put as much of the cement towards the front of the wheelbarrow as possible. It's much easier to lift. Okay? Because basically what I'm doing is changing the resistance distance. If you load up the front of the wheelbarrow, you can lift the handles much easier. Okay? And that made it easier to move. Okay? Again, another example. That's a second class lever. You're pushing a great distance to lift that object. However, you can use less force. You ever use one of those? I don't know. My family, around Thanksgiving and Christmas, they get that big basket of random nuts that nobody really likes that much, and then you have this nutcracker in there, and then the little pokey thing. And I've never seen that. You know what I'm talking about?
My sister's definitely
That's all I do
allergic to
myself.
them.
Yeah, those super hard nuts, you can hardly break them. Nobody ever eats them. They just smash them
My
up.
sister has a peanut and peanut allergy, so.
Oh, okay. So anyway, the way this nutcracker works, what's the nut? The resistance. What's this part?
Effort.
That's the effort, and this? Fulcrum. Okay. All right. A third class lever has what in the middle? Effort in the middle. And this lever does not decrease the force you're using. It actually increases the force you're using. But the benefit is it increases the distance the object moves. So again, if I put the resistance way at the bottom, I hardly have to lift my hand at all to lift this object high in the air, but it takes a lot of force. All the dimensions are the same. Okay? So in this case, the effort distance between the fulcrum and your effort is small. The resistance distance is large. So, I don't have it here. So, what does that mean about the mechanical advantage of this machine?
It's higher?
No,
Decreases.
It's really low.
It's really low.
it's really low. It's less than, less than 1. Right? So that means you're using more force, but you're increasing the distance things travel. So yeah, your elbow joint, the fulcrum is your elbow joint. Your muscles attach in here to your radii and ulna, and then your resistance is here. So a small pull by your bicep tendon can actually move your hand quite a bit. Okay? But it takes a greater force from your bicep muscle to lift that. If you hockey or lacrosse, so if you're playing lacrosse and you pass to your teammate, okay, what is this hand down here? That's your fulcrum. What am I doing with this hand? It's my effort. What's the resistance? The ball. Okay, so I'm exerting a force here that moves the head of my lacrosse stick a significant amount, giving my the ball greater speed. But what about the force you put in here? You need a lot. Imagine if you hold this lacrosse stick here and try and pass, right? Doesn't work, right? Okay, you need the ball here, and you change the mechanical advantage of your lever by where you place this hand. Okay. Now, could you use a lacrosse stick as a first class lever?
Yeah.
And sometimes you may. How would I do that? Yeah, instead, if I hold this hand still, okay, I can make a nice little short, simple pass, okay, by putting my effort in here and using this hand as the fulcrum, right? And so you're going to be able to make a pass, you can move that, you can exert less effort, takes more force here, but what happens to the speed of your ball? Goes faster. Right? So, you can't get a great power from this kind of lacrosse shot, can you? No. You get much greater power from this sort of shot. All right. Same thing for hockey stick, same thing like if you take, I guess, I don't know hockey very well, the wrist shot, right?
Yeah.
That'd be a flip with this, that's your effort is here. Okay, that's a third class lever. Okay. I mean, you don't shoot hockey like this, right? So those are examples of third class levers. All right, last thing here, power is a measurement we have, a calculation we can make of how fast work is being done. The formula is simply the amount of work done divided by time it takes. We also have a special unit for power. It's called the watt. A watt, like you've heard of watts in terms of light bulbs, how much energy they consume. Okay? A watt is 1 joule of work per second. So a clothes dryer that does 15,000 joules of work in 3 seconds has a power of 5,000 watts. Any questions about levers?